Okay, good afternoon. We probably should get started with this afternoon's debate, which looks like it's going to be a continuation of yesterday's debate. So the topic today really is on quantum computing, mostly looking into the future, but I guess we're going to talk about the state of the art today. We're going to keep the format today a little bit more free-flowing. All of the panelists are going to give a brief statement in the beginning, and then we're going to open it up for questions both from the audience and also between the panelists. So without further ado, should we get started with the protein from the second row, please?
No. I'm pro-quantum computers. The part about general purpose seemed to get started later on. So I'm just saying pro-computers and leave off the general purpose. So I would say quantum computers are here now. They just don't have any qubits. Okay, so they're used in communication systems mainly. Okay, I think that they'll continue to be used for that. I think that as the quantum repeaters become functional, we have to start purifying the entanglement. We're going to need them, and I think they'll do something there. How much is not clear yet. I've worked on quantum computers for maybe, I don't even know how many years, maybe 15 or 20. I've never worked on Shor's algorithm, okay, because I didn't believe in it. I have worked on things like lattice gas quantum computing. So the D wave is very similar to that. You have a low level of entanglement, there are lots of qubits interconnected. Those are very good for simulating quantum systems. So I think that's a niche application. Whether the sponsors are going to, push on that is another question. But I think that's a viable future too.
Okay, thank you very much. I should mention that there are a couple of panelists who are not solidly on either side. You might see them fluctuate a little bit between pro and con, and Professor Abbott is one of these, probably more on the pro side at this point. So please.
So I've asked to be a superposition of pro and con, so I'll do my best to do both. Well, my view is that quantum computation, I agree with Phil, cannot be a general purpose computer. And there's a simple reason for that. A theorem has been proved in the literature that to make an arbitrary operation on n qubits requires 2 to the n gates. That's an arbitrary operation on n qubits. So I'm not talking about specific operations like as in Shor's algorithm, etc. I'm talking about any general purpose arbitrary operation. So that immediately counts quantum computers out of general purpose, and that's in the literature, it's accepted. So that question, I think, is out of the way. So now, as for the rest of quantum computation, qubits exist, and we can do measurements on them. We can do interesting things, and from my viewpoint, is it's very important research. It's very important fundamental science. It's something you have to do anyway. And whether you can ultimately scale them to produce useful applications or not, I don't really care. It's the fundamental science that matters. I suspect you can't fundamentally scale up qubits to make a very large-scale quantum computer, but that's just my suspicion. I would like to be proved wrong. And my reason for believing that you can't scale it up is simply that quantum computation on a large scale is having your cake and eating it. What you're trying to do is isolate qubits from their environment and yet interact with them all at the same time. So you're trying to do two opposite things all at once. And to kind of have that kind of optimum medium where you're successfully in that sweet spot is okay on a small scale, but once you start scaling up and you have thousands of gates on there going up and down, creating spikes or whatever, upsetting the environment, I find it very hard to believe that you will be able to control what's going on with that level of complexity, even with error correction. So, so yeah, but having said all that, I still believe it's good fundamental science. It should still go ahead. And one motivation I have for wanting to see them scale up qubits to higher and higher amounts on a piece of silicon, for example, is that there is actually, in the literature, there's actually a cosmological upper bound for quantum information. And it's what's called the holographic principle. So once you start getting, say, around 200 or more qubits, then 2 to the power of 200 will start being of the order of the number of particles in the whole universe, and that's where the, this cosmological upper bound will start applying to your little quantum computer. And so your little quantum computer on your desk could actually test some fundamental physics about the whole cosmos, even though it's a little thing on your desk. So you could get the whole cosmos on your desk. And I think just testing this this upper information bound in the lab, I think would be awesome. So forget all the hype, forget about all the fancy things you might be able to do commercially with quantum computers. I think it's a very nice piece of fundamental science.
Thank you very much. I have some questions about it, but I think we need to go home. Dr. Kirk, please. Another superposition, right?
Sort of, yeah. First of all, I just have to start out by admitting my own ignorance on the topic, so probably can't go as deep as some of the other panelists. I am a bit skeptical of the concept of this scaled quantum computation, but at the same time I have a lot of curiosity about this D-wave computer and whether, okay, if it's working on the concept of quantum annealing, is quantum annealing really quantum computing? And maybe that's some question that can circulate wider and be addressed. So I'll just leave it at that.
Okay, thank you. We heard earlier today from Professor Dyakonov, and please.
Yes. I think that we should first define what we understand by quantum computer. What is it? Well, for example, this D-wave machine, this is something quantum, and we don't know much about it, but it is certainly not the quantum computer that is discussed in all this huge literature. It's not what thousands of people are doing during the last 15 years. So, for me, the quantum computer is this, what the thing that does Shor's algorithm, so many qubits, where one does error correction. Well, the thing that is described in the huge literature. And so what the professionals in this field say, first, that they have proved that it is possible to build one. You just must put more effort into this. And that we can make error correction. It is scalable. They believe in this. And not only they believe, they say that it is proved. So this, I think that all this is not true. They have not proved anything, really. They don't take into account a number of important issues. So I think that this quantum computer will never be built, never be scaled, will never go farther than several qubits. So I think it's a blind, it's a bust.
Dead.
Blind end. As to other possibilities, well, I do believe in quantum mechanics. It's certainly true. So there already exist many applications. continue to exist. So if we mean, so what we're discussing? If we are discussing this, the object that is described in all this huge literature, this object, I believe, will never be beyond several qubits and will never function. No error correction and so on.
Okay, we'll finish with the panel, Professor Kish.
So my motivation was, when I heard about the quantum computing issues about 2001 or so, was that time the understanding was that quantum computer would calculate without energy dissipation, because that time it was a lot of problem with the heating computer. They said, oh, our desktop computer will be taken over by quantum computers. There is no energy dissipation. You can calculate for free. And that just didn't make any sense for me. Especially that I know that if I have a resistor which has thermal noise, if I cool down the resistor so that I get into the quantum region, then actually the thermal noise will be much less than the quantum noise. So it's, if you move between a quantum region and a normal classical region, then you see that the noise is bigger in quantum region. So that how can it be less energy dissipation? That was like my motive to explore a little bit, and then with Giulio G. Vanacocci, he's an associate editor of Physical Review A for Quantum Informatics. We wrote a paper together where he used his famous formula. In 2002, he published a famous paper, which became famous, but is not really cited actually by the quantum people, quantum, or the mainstream quantum computer developments, because it's not popular. The result, it says that the title is Minimum Energy Requirement for Quantum Computation. This Physical Review Letters, 2002. Here he gets a formula that the minimum energy to operate a quantum gate, a single operation, is h times the frequency, that's clock frequency, divided by the error probability of the gate. So that was the first time when error came explicitly in the equations. This looks like as Heisenberg answered the principle enriched by errors. This is a very sympathetic formula, and this shows that the error is scaling, like the energy dissipation is scaling with the inverse of the error. Now, if I compare with the classical, in classical gate, the minimal error is kT times logarithm of 1 over the error. So there's in one case there is a 1 over error in the quantum formula, and logarithm 1 over error in the classical. So obviously, for small errors, the quantum will dissipate many times more energy than the classical. So we wrote a paper, we compared that. He is expert of quantum computers. He even visualized some concrete prioritizations with error correcting and so on. And we suppose the same clock frequency for the two computers, same performance. Both of them is universal, general purpose computer. It turns out that the quantum computer was dissipating 1,000 times greater heat than the classical. So this question was solved. Quantum computers will not take over desktop computers. Then what remains is special purpose application, and that may fly. I also don't believe in Shor algorithm for the very same reason why Professor Dyakonov. But I agree with Hammer that there are systems which can be used. Just like analog computer, there are quantum systems which could be used for nonlinear operations, calculating some simple, modeling simple situations, like a laser. Strongly nonlinear device, you could input some light, modulate whatever, you get some solution of certain things. So that's possible. Quantum systems can be used for some simulations. That's my opinion. Thank you.
Okay, thank you very much. I think what we'll do, rather than going back and forth between the panelists, we'll open it up now. Judging from yesterday, there shouldn't be any trouble getting a lively discussion going. So I just want to open it up now. Are there any reactions to what the panelists said, or any questions that anyone wants to ask the panel? Yes, please.
When you say you don't believe in Shor's, what about the implementation of Shor's? 15, 21?
A little bit louder.
they've used small-scale quantum computers to factor 21 and 15 into their primes. So what is not to believe about that? Is it because of the scale? It's not a large number?
Are you asking me?
Or any, I mean,
Well, I can answer that. The thing is, when I said I didn't believe in Shor's, I meant that you could never beat a PC with a quantum computer for Shor's algorithm. So the small scale ones, yeah, they do work and they are based on quantum computers, but the PC can beat them pretty easily.
Sure.
So the motivation.
but the time steps are much less, right? You mean in terms of real time, less time than a classical computer?
No, you know, first, as I said today, the results in factoring 15 and even recently 21, this is a sort of cheating. It is the so-called compiled version, where you use your knowledge of the answer. The full Shor algorithm was not done neither for 15 nor for 21, for nothing. Now, if this would be easy it would be done already. So the space increases exponentially, like 2 to the nth. So if you want to factor 123, it is not 10 times more difficult than to factor 15. It's many more times. So I don't see any perspective. But this is the real. Why was everybody so excited to start? Because Shor explained that his algorithm does it faster, or faster theoretically, meaning that the number of operations that you do, that a laptop does, increases exponentially. Increases like the number itself. While the Shor's algorithm, the number of operation increases as logarithm of the number cubed. So when n is very large, it becomes whatever, even if the quantum computer works very slowly, it will overcome the classical computer for very large numbers. Now the number where the quantum computer presumably can become more efficient than your laptop is 10 to 100. Well, looking at the existing experiment, which doesn't even correctly factor 15, so it seems absolutely clear for me that we will never go. So this is one thing, and the other idea is that quantum computer will simulate quantum systems. So I cannot believe in this, and especially since it is not, nobody knows. They say these words, but they are not justified. What quantum system will we simulate? How and for what? With what reason? It is not clear. So I don't see any perspective. As I said, it cannot be built, and we don't really need it. Of course, nobody, even the most hot proponents don't talk of general purpose. It's the media that says, well, we'll have quantum internet, and we'll be able to watch more porn than we can do now. with quantum computer. No, that's not true.
Download it faster.
So can I respond to that?
Which part?
General. Nobody talks of general purpose. There are several specific tasks which we can't like that.
Yes, please.
And even for this specific task, it cannot be built. So
As this is a debate, I'm supposed to disagree with you. So may I respond? So one point of disagreement, I share some of your skepticism, but where I depart is this idea that, oh, we'll never be able to achieve anything, so let's not do it. You could easily be in that position, say, more than 100 years ago, when we're trying to learn to fly or send people to the moon.
of course.
Before we sent man to the moon, I would have thought it would be impossible. I would have been on that side. So I admit that. So we have to be very careful about that level of pessimism. Another thing is, as I said, what really matters about quantum computers is really the fundamental science, not what the media says we will be able to do with quantum internets and blah, blah, blah. It's the fundamental science. And I see implementing some qubits as very interesting fundamental science. It teaches us about quantum mechanics. It teaches us about how to manipulate matter at the quantum level. It answers questions as well. For example, when you do the double slit experiment, everything you do, anything you try and do to try to decide which slit the particle went through stops you from knowing that. So you never really, any experiment you do never really tells you what it really did. So you never objectively know what happened. You know that something spooky happened with the double slit experiment, but you're not quite sure what. But you see, if you can then use superposition as a resource with a few qubits and then manipulate that and actually do something useful with the superposition, it tells you that that superposition is objectively real from a philosophical point of view, and therefore it tells you that the particle really did go through both slits in the double slit experiment by implication. So I think that's an important thing to be able to say that, to be able to say. And you can say that by building a quantum computer. And as I said, there are other fundamental questions like the cosmological upper bound for quantum information. You could test things about that on a quantum computer. So you can test some fundamental physics on it. I think that's important.
Yeah.
To the other side now. Or any more questions?
No, I disagree with one point, that this is that quantum computer, supposing that it is built, that it will help us in understanding science, quantum mechanics. I don't think it is true. In the same way as building, a rocket didn't really help us to understand better classical mechanics. It was understood quite well, and the rocket was based on the basis of classical mechanics.
Can I interject there?
The quantum computer is supposed to work on the basis of quantum mechanics. Quantum mechanics is good, correct, and it is tested in millions of experiments already. To understand atoms, nucleus, superconductivity, whatever, using quantum mechanics. So the fact that you have 10 or 100 or 1,000 qubits doesn't say anything more. In ferromagnetic, you have those qubits by billions and billions. They work as predicted. There's no problem. There's no problem with quantum mechanics. So.
Okay, so if I can respond to that. Okay, so the rocket might not have taught us any new physics, but it it verified it. It was experimental verification that you could escape orbit and things like that. Also, as on top of that, it gave us huge advances in engineering. It had lots of spin-offs, and the same will happen with quantum computers. The more we study quantum computers, the more spin-off technology in the area of electronic devices we will get. For example, the groups that are
Say one example. Say one spin-off.
So, for example, the groups that are working on implementing phosphorus qubits in silicon can very precisely place phosphorus ions in silicon, and that precision can then be used for other kind of nanoscale devices, conventional electronic devices at a very small scale. It doesn't have to be used for quantum computers. And that's the same thing for all science. No matter whatever research area you're in, whether you're studying social science, physics, chemistry, maths, whatever, maths groups, things in maths that you think nobody's ever going to use, surprise, surprise, 50 years later somebody starts using what you've been working on because you were following a fundamental path. I see nothing wrong with that.
But like the example with the phosphorus-doped silicon, was that really driven by the pursuit of a quantum computer, or was that sort of a technique that people were already using because they were trying to downscale traditional MOSFETs,
No, that was
sub 10 nanometer range?
No, that was absolutely driven by the desire to make a quantum computer. I can confirm that because it was done in Australia.
In principle, any human activity is useful, and of course we should remember that all chemistry came from the attempts to make gold from urine. And all the chemistry emerged as a result of such efforts. So, but still, it doesn't. Nobody would deny that this idea was false.
Okay, are there any other? Yes, please.
So I want to understand how much this point of view against the quantum computer is related to maybe an Einsteinian kind of way of looking at quantum theory, in the sense that, for example, today we saw this movie, there was this guy saying, oh, this mumble wave particle dualism. I was saying, what? If somebody can say that there is no double slit experiment, he said, if he has a way to explain it, it's welcome, because nobody succeeded, including Bohm. So, and I should say one thing. I'm not sure that we will have a quantum computer, but one thing is for sure. If we don't believe in quantum theory, then the quantum computer is useless. But if we believe it, technology is going sooner or later to confront quantum theory in a serious way, with nanotechnology, superconductors, and the point is that we have been teaching for years that in quantum theory you can prepare the states that you want, and then you can measure the observables that you want, and then you can perform the unity transformation that you want. But we didn't have the slightest idea of how to do it. Now we have a very precise route to follow that says how to do it. And we have a technology to do it, a real technology to do it. Nonlinear optics, atomic physics, and so on. So if one day we need an entangled state for some technology, we can do it. And this is thanks to quantum information and to the dream of achieving a quantum computer that maybe will not be achieved so fast, but it's undeniable that we need entanglement for technology. Or we just take quantum theory as a source of noise. But this is an old way of looking at quantum theory, like a negative theory, not something that we can harness, that we can exploit. So if there is somebody who says, yes, I hate quantum theory, then I say, okay. Then I hate classical theory. Okay, but this is a kind of religion, I think. It's not
I see the opposite trend. If something is not quantum, then not to fund, because quantum is a miracle, it's a magic which makes miracles. And so if something is not quantum...
But this is true.
No, but yes, because you are quantum scientist.
Classical is too trivial.
That's not obvious. So, for example, they said that you cannot do secure key exchange classically because only quantum physics can be secure. And if you have a wire, on the wire you can measure voltage and current. That's classical. No way to communicate, exchange a key securely. And we proved that by classical physics, just using thermodynamics is possible. So this is not the same. It says, what I see, this hype is all about quantum. Too much hype. And also the people who have the large grants, they basically try to cover it up. So we have heard yesterday propaganda statements that everything is fine, we are great, progressive revolution going on, 5 qubits, 10 qubits. In 20 years we have a lot of more. 10 years ago we had a debate in Santa Fe at Fluctuation Noise Symposium, Future Quantum Symposium. It's also the same thing, like 20 years.
But you believe you believe in quantum theory, and you believe that sooner or later the technology will need to use it.
It's using.
It's
used.
Many people say it's not true. I asked many people.
It is used already.
Using quantum theory.
A superconductor is a huge entangled state.
Okay.
And this was known. This was known since Schrieffer, Cooper,
Bardeen.
And when we use
57,
and when
50
we use
years ago.
technology, we are using the entanglement. We are using the real quantum feature.
But when we're using superconductors, we're using an entangled, strongly entangled state.
We needed the technology.
Not of 5 qubits, but of 10 to 24.
But I'm not talking about the microscopic theory. Not because the microscopic theory.
But it is an entangled state. It is a real
I'm
quantum
talking
state.
about engineering the quantum. Exploiting the quantum, not describing the statistical mechanics with
Laser pointer, that's quantum. It's a quantum state. It's a quantum device. It's engineering.
But laser is pretty classical light.
What?
The laser light is pretty classical. It's coherent.
No, it's quantum. It's a quantum device. Quantum device.
Yeah, it's quantum as long as you consider the interaction with the matter in special situation. But as light is classical in the sense
no,
that
because
it's a coherent state.
That's why Marlan Scully got famous when he was a student, that he solved the problem of the quantum noise of the laser. It turned out like factor of 2 times bigger than what Einstein predicted by semi-classical means. So this is.
But the problem of the quantum is not that is the way particle dualism, the humble mumble. So the laser light is perfectly coherent, is wave, right? With a very long coherence.
Yeah, but the system is a quantum.
Quantum in which sense?
The system generating the laser is a quantum device.
If you squeeze it, then it
instead
becomes really
explain
quantum.
the photo effect by introducing the quantum. So we see this quantum in very simple experiments.
So the photon is quantum.
The photon is seen. Well, absolutely no problem with quantum mechanics or understanding quantum mechanics.
Yeah, but this is not
it's
what
absolutely
I say.
clear. There are millions of experiments.
Okay, but this is not what I
entangled
say.
state and everything.
So what I say is that there will be some point in which we need to prepare a state in order to get some tool. We need to prepare a unitary in order to get some tool.
To get what? That's the question.
Forget what?
To get
For example,
to get what?
for example,
Quantum computer.
for example, I have a huge list of examples, but for example, go back many years ago when the first time where they found a way to make a line width narrower by, for example, putting an atom in a cavity and getting the spontaneous emission going down, and you can do it by squeezed light, by squeezed vacuum, or you can do it, you know, these are quantum things where you are engineering something quantum. The down conversion of radiation, quantum optics. Quantum
so
optics.
you see that
Overline detection, heterodyne detection is quantum. It's not
Could I suggest that maybe we focus this discussion more on quantum computing as opposed to talking about quantum phenomena in general? I think for this audience, I think we can assume that quantum mechanics
everyone agrees.
Yeah, everyone agrees at that.
Yes.
But I think what to use a quantum computer for is a good point, and maybe shifting from the technology and whether or not we can build it, maybe we can assume for now, or for we can trim it a little bit. Let's assume, and I think we heard it in the talk before, and I just wanted to hear some more reaction about it, that we have been wildly successful. So we have a quantum computer with 1 million qubits. What are we going to do with that? And I would like to express, just to put a little controversy out there perhaps, to be a little provocative, given that thousands of people literally have been working on this for 20 years now, there is really no good idea out there, as far as I can see, what you would actually do with a thing like that. And so I just wanted to get the reaction from the panel and the reaction from the audience. Maybe we can explore for a little bit this kind of aspect. So were you going to comment on that, or?
Yeah.
Yeah.
I think a good example of an application would be AI. There's some algorithms that show that it's called graph isomorphism. You can compare graphs quickly, then it's sort of comparable to human intelligence, where we're constantly weighing very complex systems that can immediately understand what we're dealing with, whereas computers, it's an NP-complete problem, it's exponentially slow. So they've shown that that's equivalent to the adiabatic, quantum adiabatic algorithm. So if you have a quantum computer, you can run these graph comparisons very quickly, and then you can extrapolate, maybe you can build an AI. So it's just like a general intelligent being. So that would be interesting.
So classical computer cannot do that like that.
It can do it, but slowly.
But how about the human brain? Is it quantum?
Well, no hurry.
I think so.
So human brain would be quantum.
I think everything is quantum. I think this chair is quantum.
But the definition of quantum computer is that in this case you need entanglement. Do you think that there is entanglement in the brain?
I think there's some, I don't know in detail, but I believe there's some experiments to show that there actually is imaging where in the brain there is immediate correspondence between reactions in one hemisphere and in the other, even without they're entangled. They're operating. They're not shooting information slowly across from one side to the other, responding. They're actually operating simultaneously.
That's not proven. Let's suppose that case maybe there's a common source and reaches that part of the brain at the same time. So that could be just.
So I mean, the universe is quantum, right? Fundamentally, and we exist in this quantum field. So why would the most advanced thing that we are aware of in the brain not be a quantum device?
The temperature is high.
Yes.
36 Celsius.
Yeah.
Well, I can answer that question. There is some entanglement that goes on in biological systems that's pretty well documented. The magnetic sensing is quantum in nature. There's entanglement there. Okay, whether that entanglement, how much it helps is a question, but it's there. And so when we talk about the quantum computer, the question is, what's the level of entanglement? And the same with the brain, what's the level? Most people think of quantum computers, they think of global entanglement. But that's pretty much not going to happen. Okay, then the question is, if you have less than global, if you have local entanglement, can you do something? And the answer is probably yes. And in fact, that's how I got into quantum computing. I got into it for a lattice gas quantum computer. Now, those of you that aren't familiar with lattice gases, what you have is you have processing nodes which have nearest neighbors, and they're arranged in a lattice. Okay, and using only those nearest neighbor interactions, they simulate macroscopic things like fluid flow. So there was a lot of interest in the community to speed that up, because right now they can only model very simple fluid flows, but they want to model very complex flows like over aircraft and maybe even simulate the weather. Okay, but that's way beyond, because the complexity increases very rapidly. So they wanted to see if a quantum computer could beat that. And so that was the project I was involved in, was to try to see if that would work out. So we proposed that we would build a 100-qubit quantum computer with entanglement and try to speed that up. So the bottom line is we didn't quite get that far, okay, in 2 years, for the amount of money we had. And in 10 years, and with way more money, D-Wave has gotten there. Okay, they're basically, it's very similar design to what we had planned, okay, using different materials. Okay, so the hardware is out there now. Okay, but then the question is, we did some theory, and the theory turned out a little disappointing in the sense that we were hoping for exponential speed up of this lattice gas. Turned out the best you could do is quartic. And that's only if you had global entanglement. And so if you had nearest neighbor entanglement, how much could you get? We were hoping for at least quadratic. But even that would make a big difference in terms of simulation of turbulence and things like that. But of course the sponsors weren't impressed. They wanted exponential. So there was one lattice gas program, then it died. And in fact, D-Wave had to get their money from private sources.
So there's many applications.
Yeah.
No. You must be more precise. The question is the question that our chairman moderated posed was, suppose here you have a quantum computer. So what are you going to do?
Oh, but you won't have a quantum computer unless you have a problem.
And you must keep in mind that it is not, and nobody is a specialist, do not say that it is a programmable computer like your laptop. You cannot make a program to calculate something, some profile of something. That's not what it is for. So what are you going to do, and why it will be better than do the same thing with the
Well, yeah, you have the problem. The way quantum computers work is you have the problem first, and you build the computer to solve the problem. So in my case, it was lattice gas. In D-Wave's case, it's Ising model, or the traveling salesman problem.
But actually, what I was asking is something. I understand where you're coming from, but what I was really thinking is, assuming, given that people argue that we need to have a quantum computer, it just happened. So a quantum computer now is an object that has, say, 10,000 qubits, or maybe a million, or whatever number you want. It's capable of entangling any 2 qubits in any way you want, which is sort of the dream of the quantum computing community, it seems to me. And it happened without having any application value. But this thing exists. So what would you do with it?
Oh, you use it to simulate weather. You get the quartic speed up with the lattice gas, and you simulate weather.
How would you simulate weather?
It would have a high enough Reynolds number that you could simulate weather patterns.
No, once more, it is not an object where you can say, we can give a program, calculate this. It doesn't do it. It's not designed to make. It is not a normal computer, but more powerful. It's a different island.
It's an analog computer, and it should be actually compared to an analog computer. So it's completely unfair to compare the speed of a quantum computer to such a general purpose computer. Question is, if I build an analog computer for the same purpose, you build a quantum computer for the same purpose, what is the speed difference in the question?
This is the general misconception that media induces, that this will be like a normal computer, but unimaginably more powerful. That's not true. It's not like an ordinary computer at all. You cannot watch video on a quantum computer. You cannot calculate the profile of a boat, which gives lower resistance and things like that. It's not designed to make these things.
Can I give another
Simulating
application?
spin chains, that's okay. If this will be...
So there is an application that everybody is forgetting. So, as I was saying before, the quantum computer is a way to achieve, to engineer transformation, to engineer observables. And this is a way to improve measurements, to improve many, many applications. There is an entire section of quantum information theory that is optimization. Optimization of process. For example, if I send a reference frame, I can send it in a quantum way, and then it becomes much more precise than if I send a classical system. There is the whole technology of quantum interferometry, which is very popular. So if I can engineer quantum transformation and quantum state, I can have much more precise measurement, much more precise. I have a whole field of technology that becomes very precise, and I don't need to build up a big quantum computer to do that. I can make things much more precise with just a control knob. So I think that the technology is pushed in the right direction, even though we maybe will not achieve the quantum computer that we dream in a normal time.
I think the question, however, was what would we do with a million qubits?
A million qubits.
That was the question, and my take on that is if you had a million qubits, you would only use 1,000 of them anyway, because the rest of them would all be error corrected.
Not in the lattice case.
And then what would you do with that? You know, who knows? It's fundamental science, and people didn't have the vision what we would do with our normal computers, say, back in the 50s. They never believed we would have things like laptops and have all that power. So I think we shouldn't second guess what's going to happen with quantum computers if it should get to a million qubits.
But thousands of people are trying to develop quantum algorithms since 20 or 30 years, and we have only 2 which works. Okay, they suppose that we have the computer, and they're trying to develop algorithms, and that is just 2. One of them is useful. I mean, sure. Growers is nothing. Yes, it's just interesting.
Sure, it's also
Yes, interesting.
I don't know much about quantum computer, but I'm coming from Japan, and we are suffering from Fukushima incident. And if there is a computer that anticipates asking for the safety of people, that is the same interesting.
So why does it have to be a quantum computer?
I don't know. It does not have to be a complete quantum computer, but that is currently impossible. So real world is so uncertain.
If the people quit to drink and to smoke, we're much more healthy.
What I want to know is to know the incidence of earthquake before it happens. It is pretty much socially required.
Problem is that's not a computational problem because the substance is
Yeah, exactly. Yeah.
So the medical one with this protein folding, you could compute drug discovery and creation, which is very computationally intensive now. So there's quantum algorithms for that. And then to the search, Grover's is useful because if you have an unsorted space, like a distributed system, a decentralized network, it's like the internet, and you want to find something, that Grover's is excellent. It speeds up that dumb process, that unsorted resource search. So
But it's a very small speed up. It's not exponential.
no, but square root.
Square root.
Good.
Oh, here that's true, but well, that's evident. So you have a normal computer which computes very fast. A quantum computer will not compute fast, it will compute slowly. How slowly I cannot tell you, but it will be orders of magnitude slower than the light. So when n is n or square root of n. So you have n with a large prefactor and square root of n with very small prefactor. So eventually for very, very large n, it will overtake. But before that, it will not help, it will be slower. So it's very, very large n where it may have advantage. Building just for this purpose as to protein folding and all other problems that you are talking about. There is no prescription how to do it. It is not obvious that having a quantum computer you can solve protein problem. No evidence whatsoever. So let somebody, before building the computer, first let somebody explain how should we solve protein problem with this quantum computer. There is no such. There are many good things that one would be good to do, but there's no evidence that the quantum computer will do those things better.
Yes, please.
To my understanding, any problem can be formulated as a search problem. So in that sense, every problem can be moving faster than a quantum computer. In that sense, we can split up on every problem.
Does anyone want to comment on that, the computer science?
That will probably Monte Carlo stuff. There are better ways to do things.
But is it true that all mathematical problems can be formulated as search problems? Whether it's the best way or not?
Probably Monte Carlo, at least a lot of problems can be formulated in Monte Carlo, but it's very inefficient in most of the cases.
So it is being said, and that if it can be proven that P is NP, that mathematics can be done by computers. So if you believe that NP-complete problems can be solved efficiently by quantum computers, maybe you can say mathematics can be done by quantum computers. But as far as I'm aware, no NP-complete quantum algorithm has ever been designed, and I think they don't expect it to be. And the reason is that NP-complete problems are very irregular. They cannot be cut in subproblems, and integer factoring has some regularity in it. So it has never been proven even that integer factoring can be transformed in an NP-complete problem, and they don't expect it to be. So I don't expect NP-complete quantum algorithms ever to be designed.
It's non-linear quantum algorithms which achieve NP-complete computation. Like there's a search algorithm which uses non-linear quantum and it achieves constant time search, not square root of n equal 1. So, but you need a non-linear quantum computer, which implies you need to separate exponentially close states, states that are almost perfectly parallel. So it's unknown if a quantum computer can do non-linear quantum. It's all open questions. It's even unknown whether a classical computer can do quantum computation efficiently. It's also an open question.
Is there no linear quantum physics?
What's
Non-linear? What do you mean?
I'll link you to this paper. It's Gross-Pitayevsky algorithm.
No, it's the Gross-Pitayevsky equation, but words for describing the liquid helium. Super fluid. Oh, there's not much to solve. This thing can be solved on a normal computer. But there's no great need to do it.
These authors, I don't know the details, but their finding is that his name's David Meyer.
It's not that quantum mechanics is modified. It's that specifically this superfluid is phenomenologically described by the Ross-Pitayevsky equation, which is nonlinear. Nonlinear equations are not a problem for the laptop.
Right, but they're achieving search of an unsorted space in constant time. So the amount of time, the size of the list to search is the amount of time to get the answer is independent of the size of the list. So it's quite, it's proves, faster than light travel and all these breaks, causality and all these things, but you need this kind of non-linear quantum computer to achieve this.
Probably they leave out the noise. Always this magic stuff that happens when they neglect the fluctuations, and then a lot of magic stuff can be broken. So it's not a real system, but they study that. But like idealized system, which is not real. That very often happens.
So there seems to be some, I wouldn't call it consensus, but some support to the idea that search might be a large class of problems that the quantum computer might be useful for. So let me just follow up on that a little bit more and try to get a little bit more specific. So the question that I would like to pose now is, assuming that search is the killer application, and also realizing that a quantum computer, of course, would have to compete with conventional technology, which is not going to stand still, obviously. So can I just ask for some predictions? Just put some numbers on there. So in order for this to be useful, for a quantum computer to be useful, how many qubits is it going to take for some real application? How long is it going to take, or when is this going to happen? And then maybe if someone wants to comment or speculate about how much energy that would take, what the power dissipation of a thing like that would be. But I think the primary characteristics might just be how many bits might it take, qubits, and by when this might be achievable. And then I guess we can also comment on where's conventional technology going to be at that point, right? Is there something that I can get some reactions on?
You should specify, as you said, the useful bits and those.
I'm talking about
correction, which is the majority.
I'm talking about the useful bits. And then we have to multiply it by whatever factor is.
Not multiplied, but squared or cubed.
Okay. Let's talk about the useful bits.
So if you have 100 useful bits, that means that you must have either 10,000, between 10,000 and a million.
So how many useful bits which are actually going to be important for the calculation? So does anyone want to venture an opinion?
Like if you wanted to solve turbulent flow over an aircraft, how many?
Oh no. I think these kinds of problems are not going to be, but search is probably a large task that the quantum computer might be using.
So I have a problem with the Grovers actually. Before.
Okay.
Because my understanding was that for Grover, like phone book, whatever, you have to read in the information into this memory before you start the search.
Yeah.
Now, what a computer scientist would do nowadays, if that happens, there's a lot of research on large databases and large database searches. There's current hot topic. They would do, when you read it in, they would hash the data. Hashing, basically like indexing, but it's like an exponential way. Okay. So that would be like searching, for example, like this, much faster than any Grovers. So during reading in, the data can be prepared so that a classical algorithm is much faster than Grovers. So I don't see actually the relevance, because you have to read the data in before you search. Okay.
So you're saying that a quantum computer, for the reasons that you mentioned, won't even be of interest for this search application?
It looks like, unless you can do rovers without reading in the data.
Once the data's been read in, and people are using it, you can talk to searches.
Basically, you hash it, you put it in the categories, like in a power function, and it's very easy. Just infuse that, you find what you're looking for.
I'll just mention something. I don't have any real detailed knowledge about this. I'm barely doing more than repeating something I've heard, but I understand that that the D-Wave that D-Wave is inviting people in the community who want to solve optimization problems to work with them to answer the question of how do you program it to do certain things. And of course, I have no opinion on whether it's a quantum computer or not. I don't know much about it. But if the question came up, this was two questions that came up. What's the application? Optimization. There's lots of optimization problems that are interesting to people. And apparently, that computer has already been used for some protein folding work. And there's also, I've been told, they sort of have a program where they work with individual people who want to use it to work with them to try to figure out how to program it to solve particular problems. So does anyone else, can anyone else speak with any actual authority on that? Do you know so?
Well, I just know what I read about. I haven't actually interacted with them or anything. And I know the design is not very different than what I originally proposed many years ago. And the level of entanglement is probably not very high. And that doesn't seem to matter for some of the simulations they've done. They seem to get results that look like the results they would get from a quantum simulator, even though the entanglement is very low. And there's no error correction or nothing like that. So I guess we don't know. That's probably why they're asking for ideas. If we don't know how much entanglement is needed to be useful, how much error correction is needed to be useful for solving problems.
To go back to your question about how many qubits starts becoming useful, well, 2 to the 20 is only 1 million, so that's not very useful. 2 to the 30 is about 1 billion. It starts coming to be a little bit useful. So you're looking at the sweet spot somewhere between 2 to the 30 and 2 to the 40 to get started. I doubt one ever needs to go more than 2 to the 200, because then you start getting to the order of the number of particles in the universe. But then you've got to look at all the error correction gates that you have to put on top of that. What was your question after that?
When?
Okay, so to get to over 2 to the 30 plus the error correction, I'm fairly pessimistic. So in the next 50 years.
Well, I think if you
You're
look
saying
at
30 qubits plus error correction.
Yeah.
I think if you have 2 qubits plus error correction, you can do really useful things, provided those 2 qubits are hundreds of kilometers apart.
Well, as I said in my talk, 1 qubit and error correction that preserves this qubit, that would be already something.
Yeah, and if they're hundreds of kilometers apart,
no,
you get
no
2
use,
kilometers.
no practical
but if you had 2,
applications.
they would have
Just
practical
it would be interesting
Yeah.
by itself.
But if you had another one, then they're very practical applications. You put them hundreds of kilometers apart and have a very high degree of purification. Then there would be applications.
I have a probability question. So, what do you think, Michael, when would sponsor kill the topic? I mean, when would sponsor stop sponsoring quantum computing?
Stop sponsor?
Yeah, as he said, okay, it doesn't lead anywhere, so let's kill it.
That's a question. I don't know. It's a social.
Yes, but
I can answer
No,
that.
but in response to this question, I say never. There
Yes.
will never be anything useful.
Well, that's pretty clear, yes.
I can answer when the sponsors will stop funding. I don't think they will. They haven't stopped sponsoring nuclear fusion. Why should they? stop sponsoring a nice bit of fundamental science like this.
They did just on junction computing, they stopped it. They stopped optical computing. All of them went for 10 years or something, then it was over, there was no use, and they stopped it.
Yeah, but this is an area which can have technological spin-offs.
That was the same saying. As, for example, for optical computing, something came out. Military is using optical Fourier transformation. That was the only thing that remained in the military, and then they forget. They are not using it. So they stopped it.
Yeah, the typical lifetime of a technology, at least in America, for the military is about 20 years. Sometimes you go as long as 30 if you're getting good results. But usually 20 years, the sponsors lose interest and want something new and more exciting. And so quantum computing is past that now. So they expect to see a quantum computer working or else. And that's what IARPA is doing. They have a huge program. They want to make a 100-qubit quantum computer or else. And they want it now.
So they sponsoring it right now, or?
They want a 100-qubit quantum computer or else.
In what time?
And well, a few years. They're putting lots of money into it right now.
Without error
3
correction.
years?
Well, the error correction there too, yeah.
So if they don't get it, then it will be over.
I think that it's going to stop. Yeah.
5 years, 10 years?
Well, however long the program goes, and, until they get, I guess the program would be a 5-year program.
I see.
You know, before this craziness started, 94, before Shor's paper, there was already a marginal activity in quantum computer. Deutsch, the father of quantum computer, was in 85. Nobody knew of that. So there was a very small group of enthusiasts who quietly worked on this without no noise, no media coverage. So I believe that this will return to this state. There will be people who will continue working. Nothing dies out completely. Even the optical computer is not completely dead. So it will return to a normal state. All this craziness, this hype will go away. I don't know when.
Well, I remember when that...
Well, as you said, 20 years is a typical time. Well, 20 years will be next year.
Yeah. I remember before quantum computing, and at that time, the funding was being cut, and basic research in physics was on the way down. Suddenly, quantum computing, basic research in physics is needed again. So what's going to happen when quantum computing goes? Who's going to need basic research in physics? I don't see who's coming along to pick up the slack.
So what's the next big hype going to be? That's what.
Well, I don't know. Nobody was expecting quantum computing to save physics. Okay, it did. What comes next? I don't know.
But that's the general craziness of the situation. You have to make something big, really propose some big hopes, and then everybody becomes interested.
Yeah, I think Russia has to start. That's how it worked in the space race, right?
No, China will start.
China's turn.
China's turn now.
Space.
Could I follow up on one of the things that you said early on, and again in the spirit of let's assume that we're able to build a large number of qubits. You said there's some fundamental limits, like the finite amount of maximum amount of information in the universe, the number of protons. I didn't quite understand it, which corresponds to say 200 qubits. Let's assume that I'm able, or someone is able to build a quantum computer with 1,000 qubits. Are there some cosmological reasons why that's not going to happen? No, I'm not just. But this was the statement.
Yes, there's a theory called the holographic principle that if it turns out to be right, once you get over a certain number of qubits, there may be some new physics that starts coming into play in your quantum computer that you hadn't predicted.
Well, maybe,
and so,
not.
therefore, this would be an ultimate test of that. It would possibly mean your quantum computer doesn't work anymore. So, but that's not a reason not to do the quantum computer.
Derek, we can do this test with you. Noise-based logic can do it. We need a computer with 400-bit accuracy. We can do a 200 qubit equivalent noise-based logic.
But are you really getting 2 to the power of 200?
Yes. A superposition will be 2 to the power of 200. Yeah. You need 400 bit
Can you
accuracy.
deliver by next year?
Yeah, if you assemble a computer or a software basically which can handle 400 long bit numbers, then we can do it. It's very easy. And not input happen, I think.
Okay, I saw one more hand in the back.
I think maybe it ties into the whole, if you break through the cosmological upper limit, you're tapping into some kind of many worlds or multiversal resource. Because how do we know how many particles there are? We're always discovering sub levels.
Yes,
So.
exactly.
Let me tell you a short story. There's this guy, Leonid Levin, in Boston, who is a computer scientist, very well known, and he is one of the non-believers in quantum computing, and he wrote just one page of this. So he says the following thing. The proponents of the quantum computing say that this is the possibility of making a quantum computer is a direct consequence of quantum mechanics. If you don't believe in quantum computer, it means that you don't believe in quantum mechanics. Or means that quantum mechanics is not exact. And so they win either way. Or they build a quantum computer, or they find corrections to quantum mechanics. Okay, says Levin. So let's imagine the following scenario. That once we start building quantum computing, while there are 2, 3, 5 qubits that works perfectly, but long before it starts competing in factoring with pencils, the machine doesn't work anymore, and then people ask for a Nobel Prize because they've demonstrated that quantum mechanics is not correct. They've made everything, it doesn't work. But then he says here the Nobel Committee would like to have something more proof than just the non-working machine. So they would like to have some information about the state of the quantum computer. And then he says they will find that the universe is too small to measure, to find the state of the quantum computer, because the number of amplitudes exceeds this holographic principle. It's greater than the number of particles in the universe. That was Chris' story. I like it. So that indeed is the problem, because, as you say, suppose we have a quantum computer. Now, it's a black box. There's input, output. You make your input, and from output is go to hell. So what do? You want to factor 1,000 digits number, and instead it says go to hell. How shall you correct it? You must find out what is wrong with the quantum computer. Okay? When you have a laptop, you can print all the transistors in what states they are. On, off, well, there are a million of transistors. Okay, you can print it, and then look and see where something goes wrong. But the quantum computer, you can do nothing of the sort, because there are 10 to 300 amplitudes that you must know, and this is impossible. So there is no way to check, to tune, to find bugs. It is a really black box with two holes.
Okay, we're getting close to the hour and a half, so I would like to encourage any further questions or comments. Yes?
It's just kind of maybe it's facetious, but if you look at the last 100 years of progress, right, and you see, or even 100 years into the future, whatever that looks like, it's almost impossible to imagine. You're gonna, do you believe, this is to the naysayers, do you believe that we will never achieve a scalable quantum computer? There's just a lot, it's like God has said no, we can't do it. Or will we, and because we understand the science and, improve our engineering, it's an engineering problem, right? There's not really any unknown science that could be taken care of. So isn't it an eventuality, or is it just a law?
Well, let me ask. First, I don't know, of course. But second, I believe that history shows us that the really interesting, wonderful things appear unexpectedly. Nobody knows that this, nobody can imagine, and suddenly there is something new. Now the quantum computing, the atmosphere is quite, and I believe that this will continue. After some time, we'll have something really new and unexpected, and so on. This will continue indefinitely. But now we have a completely different situation. There's a crowd of people, all the media, and also we are building quantum computer. It will be something wonderful, wonderful, wonderful. Everybody is saying the same thing. This is a bad sign. When it is like that, nothing happens. Nothing. Like in the Soviet Union, during 70 years, everybody said, well, not everybody believed, but we're building communism, it's close, and this story with quantum computing reminds me very much this atmosphere of building communism. It's exactly the same. Laszlo,
Yes.
he knows. So, and this is a very bad sign. So when everybody is saying the same thing and expecting that tomorrow we'll have something, then nothing happens.
Also, this is 10,000 years, but we have all this beautiful progression. No, in 10,000 years, the Greek science was forgotten. Yeah. So this is there are here decades, and Greek science was forgotten. The Roman Empire didn't develop any science, just technology and organization, and there was the dark Middle Ages. So basically, science started sometimes again in the 14th or 15th century, yeah, and a different level. So this is it can be maybe this end of science, all this hype and that's going on, fighting for money, all this measured by impact factors and citation numbers. This is all bad sign. Maybe it's a Greek science. Roman Empire takes over and limits the technology, military technology and organizations, and scientists will not have breath. Who knows?
Okay. Are there any more? I think we're coming to a close here. So what I would like to suggest in the last few minutes, and that's going to round out the hour and a half, maybe we could just have each panelist end with a very brief statement, maybe it could be a one-word statement here, or a brief statement about, since the session title was about the future of quantum computing. So if you had to respond to the future of quantum computing and make one very brief statement, since the Kansai response is a little bit more predictable, maybe this time we'll start from this side and go down and end up on a more positive note, presumably. Laszlo, I'm going to put you on the spot here.
It will be shut down, say, I don't know, 5 years, 10 years, and there we go. Either the group will do, and Europe will follow later, and so on. So basically, it will just die out, just like optical computing. There will be some new hype, and that's it. I think that's it.
I agree.
I would just say it's irrelevant.
Okay.
And I guess I would follow up to say too that it seems almost like quantum computing's kind of been made as a panacea. For example, we have this classic computer as a really nice Apple Macintosh computer, but sometimes we give it the nickname Dumbbox. It's only as good as what we know to do with it. we know the physics of weather, or we know the physics of electrons transporting in silicon, so we can write programs, use computers to model things. But that's because we understand up front, or we at least know a path to take to do that. But then there's this concept of like taking quantum computing to say solve for protein folding, but we don't know how to do protein folding. So then the quantum computer just becomes an excuse that you can just order it, make a command, okay, I'll dump this task in and it'll magically solve it, and sort of takes the human element out of it, of having to compel yourself to understand the physics first of what you're even attempting to do.
Okay, thank you.
Quantum computing is a wonderful piece of fundamental science. It manipulates matter at the most fundamental level. It's quite different from optical computing, which is just a little bit of engineering. This is real fundamental stuff and should be funded to continue. One has to separate the hype from the reality, and the hype is an unfortunate consequence of the system we live in, and that we have to fight for funding, and the unholy alliance between editors of high-end journals and what happens between them and the funders and all that sort of thing. So hype is one of those evil products that helps to lubricate what goes on there. So it's something we live with. Maybe that it's the system that has to change, but it's not the fault of quantum computing. I think we have to stay focused on the fact it's a nice bit of fundamental science, and move on and see where it leads us. We shouldn't fall into the mistake of trying to predict the future, what it can do, because I would never have predicted we could send men to the moon. Over to Philip.
Okay, well, assuming the funding holds out, I think we'll have qubits, long distance, that allow long distance quantum communication. We'll have few qubit quantum computers, and let us get to that. We will also have many qubit quantum computers with no error correction that do quantum simulation for unknown reasons, because they don't have a lot of entanglement. They have just enough. So the two things is what I expect.
Okay, thank you very much. So this brings to a close not only this panel session, but also the meeting. I assume that Laszlo and Hay are going to have a few things to say, but while Hay walks up to here, I think I'm going to be speaking on behalf of all of us if I express my thanks to Laszlo for his vision and for putting this meeting together, for Hay, for the local organization, and I don't want to leave out the student volunteers who have been extremely helpful, and just speaking for myself, we would have been completely lost without them. So thank you very much to the organizers.
Thank you for everybody to come and making this meeting to happen. And let's hope that it will continue maybe in 2 years, maybe it will be ideal. Let's hope and have your final words.
Yeah, thank you all of you for coming here and joining this conference, and it makes me very exciting to see you in Hunan University. I hope that even our university is so old and the facility is so old, it's not improved when you stay in Changsha. I hope you can enjoy the food and stay in Changsha. Thank you very much, gentlemen and ladies. Thank you.